Hello everybody, my name is Yitong and I'll be talking a bit about our paper, Soft Multicopter Control using Neurodynamics Identification. Drones today are mostly made of stiff materials and we generally want them to be as stiff as possible to minimize the deformation. And this is so partly because the prevalent control methods assume rigid body dynamics, so any deformation will be a model and therefore surprising to the controller. And also the stiffness grants stability, thrust efficiency, and durability, which are all favorable in what drones do, such as cinematography, load delivery, and agricultural irrigation. But this last statement that I just made was sort of wrong because what drones should be able to do is not predestination, but something that's up to us to reimagine and redefine. Today, it's not just about the aerial locomotion anymore. We're looking for them to transform their shapes during flight, to squeeze themselves to pass through confined spaces, to grasp objects with their bodies, or even operate machines like human fingers can do. Recent works have showcased impressive results in these endeavors, but because they adhere to the rigid body paradigm, their methods are mostly ones of addition. They append cable-actuated fingers, different folding mechanisms, or they link together multiple copters with joints and gimbals. And that makes some of these designs really heavy in terms of both the control derivation and also literally the instruments themselves. In their approaches, these actions are sort of inevitable because for rigid materials, they don't deform themselves, right? So in this project, we seek to investigate an alternative and more natural approach. In order for aerial deformation to happen, we make our drones with deformable elastic materials. Then a soft drone can deform with just adding appropriate thrust values to their motors as shown in the animation, requiring no additional parts. However, this softness also makes the control problem much more difficult because deformation alters the rotor positions, angles, and body inertia, therefore significantly changing the dynamics. And also it's non-trivial to design a low-dimensional discretization for the soft continuum body. To build controllers for soft multicopters, we have to ask ourselves 3 questions. First, how do we represent the deformed drone, and how to describe their dynamics, and finally, how do we control the dynamics? For the representation, we want to build a state that is compact so that it's controllable by our few rotors and also measurable so that it can be used in a feedback control loop. We also want it to be intuitive because it is through the states that a pilot conveys their intentions. Our strategy is inspired by a classical idea using reduced deformable simulation, one which decomposes the full deformation into a rigid body frame and a pure deformation component. Our state representation thus consists of a position vector, a rotation vector, and a deformation vector. The position and rotation will be measured by an IMU placed at the center of the drone, and the pure deformation will be the concatenation of the angle differences between the body frame and the frames measured at the periphery, which are S1 to S4 in the figure. If you want the left and right wings to fold up, you just need to specify positive values for S1 and S3 in the goal state. We then evolve the 3 vectors with 3 separate neural networks. The training dataset will be generated by applying constant random thrusts to the drone for 1 second before new thrusts are applied. The dynamics is second order, so the network will be fed with the current state of the drone and its rate of change to predict the next frame's rate of change. Once the learning is successful, we use AutoDiff to extract the Jacobian matrices for linearization with tailored extension. Then we use LQR to compute the optimal controller for the linearized system. Generally, we need to linearize around the fixed points XU, but in our case, these are difficult to obtain, so we circumvent this necessity by using our online-relinearization. Basically, we linearize the system not at any fixed points, but at the current state, which at first is just the drone's initial configuration for X and all zeros for U. Towards the final desired state, we try to reach a waypoint state calculated by a PD control. After every 10 control time steps, the U that was computed to reach the waypoint will then be used to relinearize the system. In this way, the pilot can just input their desired shape without worrying about the stability issues, and the algorithm will iteratively try to approach it as much as it can. There are several limitations to our current approach. First, the sensor placement requires human design. In the future, we look to automatize that process. And secondly, the training for every model starts from scratch, and in the future we hope to set up a modular platform that facilitates knowledge sharing. Finally, we hope to test our approach in real life once the global situation alleviates. And thank you for your attention, and that will be it for me.